The Pythagorean theorem, it's hard to say, but it's actually really fun to work with. We only use the Pythagorean theorem with right triangles. Don't ever use it with any other kind of triangle because it only works with the right triangle. Now, it has this funny name because it was invented back during the Greeks. There was a Greek mathematician named Pythagoras, and he only studied right triangles, and he found out that there is something very special about the way a right triangle works. And at first glance, it doesn't seem like there's anything too significant. If I take a look at this right triangle, I can see that this side length is 4 units, this side length is 3 units, and this side length is 5 units. First, it's making us wonder, well, what's special about 4, 3, and 5? And it doesn't appear like there's anything special about that. But what Pythagoras did is he looked beyond just the side length and he thought, all right, well, let's take a look at the area attached to that side length. So remember, that area is going to be a square, a 4 by 4 square, which makes this 16 units. And this is a 3 by 3 square, which that makes that 9 units. And this is a 5 by 5 square, and that makes that 25 units. And so when he took a look at 16 plus 9 and 25, he figured out that if you add this length and this length together, they equal the same amount. That was the breakthrough, because what that meant is that we could then create an equation and we could solve for an unknown length of side based off that equation. And that equation we call the Pythagorean theorem. And it simply is a squared plus b squared equals c squared. Now, how does that help us? Well, number one, we can get side lengths given to us, and we can figure out if those side lengths actually make a right triangle. Now, the key on this is the two smaller side lengths go with what we call the legs. So they touch the right angle here, one going up and down, one going side to side. Those are our legs. They have to be the smaller side lengths. The third side length has to be what is called the hypotenuse. Again, it's a Greek term because this is when the Pythagorean theorem was invented. Now, the hypotenuse is always directly across from that right angle. It's always the longest length of side. So when I look at these three side lengths, I know this has to be a leg, this has to be a leg, and that has to be the hypotenuse. All I have to do is plug it into this Pythagorean theorem. So I'm going to plug 2 in for a squared, 3 in for b squared, and 4 in for c squared. Now remember, we have to square it. So 2 squared is 4, 3 squared is 9, 4 squared is 16. Now the key is if it were a right triangle, both sides would equal the same amount. But when I solve this, 4 plus 9 is 13, 4 squared is 16, 13 is never going to equal a 16. Therefore, I know these side lengths cannot make a right triangle. Versus, take a look at this one. If I have a side length of 5, 12, and 13. Well, here are my two legs because they're the shorter ones. Here's my hypotenuse. I plug it into my a squared plus b squared equals c squared. And when I solve it, I see 169 equals 169. Therefore, these side lengths have to make up a right triangle. So that's where we can start with the Pythagorean theorem. But then sometimes we're going to have a missing side length. Now, when would this happen in real life? Well, architecture. We use triangles a lot while we're building, and we don't always know what we're going to have for the lengths of our sides. So as long as I know two sides, I can figure out any one of the other sides. I could have A missing, I could have B missing, I could have C missing. But notice the Pythagorean theorem never changes. It's always the same theorem. A squared plus B squared equals C squared. Now, I know these are all right triangles. That's why I choose to use it. If these were not right triangles, I wouldn't choose to use that. So you're always going to leave whatever is your unknown is missing. Now, when I build my triangle, I just always choose A to be the one that goes up and down, B to be the one that goes side to side. It doesn't really matter because both of these are going to be on the same side of that equal sign, and because we're adding them, it doesn't matter the order that we add them. That's just my personal preference. So when I go to solve this and I plug them in, I get an equation. So a squared plus 2025 equals 2601. The second I have an equation, then I just solve it like I solve any equation. So I have to get a squared by itself, so I need to get rid of this plus 2025. So I'm going to subtract from both sides to keep my equation balanced, and I'm left with a squared equals 576. But remember, I never want to leave it as a squared. I want to know what a is. And the way that we inverse out a square number is by taking a square root. But if I do it on one side, I have to do it on the other side because we're keeping that equation balanced. And when I take the square root of a squared, I get a. And when I take the square root of 5,706, I get 24, because 24 times 24 equals that. Now, we were lucky on this one because this was a whole number. But remember, not all of our square roots are going to be whole numbers. So in this example, I'm missing my leg of b, and I plug it into my Pythagorean theorem, and I go and I solve it. And when I get down to my square root of b squared equals the square root of 124, okay, when I go to calculate that, that's not going to be a whole number answer. So what I do is I have to factor 124. And I realize that I can use 4 times 31 to equal 124. That's beautiful because 4 is a perfect square. And if I can factor out that perfect square, I have to do it. So when I take my square root, I get b on this side. The square root of 4 is 2. I can't do anything with the square root of 31 because it's not a perfect square. So I have to leave that under the radical sign. So always remember to factor those answers at the end. Don't expect to always have perfect squares coming out. And then that leads us to our hypotenuse. Well, our hypotenuse also can be the missing one. Now remember, it's got to be the longest side. So when I get my answer, I can recheck it back to see if it's actually longer than the other two. I still use the same theorem, and a lot of times this is the easiest one to solve because you're always going to have your c by itself, so it doesn't make the equation nearly as hard. And so when I take 9 squared plus 12 squared, I actually get 225. Again, we lucked out because when we take the square root of both sides, 225 actually happens to be a perfect square, and I get c equals 15, which means the lengths of sides for this right triangle would have to be 9, 12, and 15. So the Pythagorean theorem is our answer to solving any unknowns that we have in the right triangle if we're looking at the lengths of sides. It's easy to use. You just have to remember the rules of the radicals and always factoring those out. But I think you will enjoy it. Go to work, become great mathematicians.